Okay. In this video, what we are trying to do is find actually the most optimized paths between, if you want to lay down like a circulation path or like a road or any kind of a pedestrian path. You might think that between 2 points, if I take side, the straight line is the shortest path, but that's always, or probably not always, but mostly it's not the most optimized. You'll have to climb more. So you might have to meander some paths. So what we're trying to do here is I again go to the top, and let's say I focus on 3 points. These points based on any kind of data are the best, maybe because of the approach road, or maybe because of the drainage pattern, or maybe because it has less slope. It's more flatter to build here, so I want to go from point A to point B. Okay, so what I'm going to do is I'm going to use this part of the code. I'm going to take this and let's basically just do this one by one. One thing that happens is, since this is up in the air, when you make these points are going to be made here, and that's okay, that's fine. I'm going to enable this component by component or portion by portion. So I will take this and I enable this, and what's happening here is I take this as first point, and let me hide all of this. Okay, and that is my projected surface. This is my second point. Okay, and so I get a line like this. I get a line like this from these 2 points, and this is the surface that I have fed somewhere above. Okay, what I'm going to do is, first let's just find, if you see this line, let's just project it. I'm going to enable this, and it says that finding length and average, this means finding length and average slope of any path. So what I've done here is, because of project, I've projected this line here, and then I've divided it into, let's say by default, 10 parts. And then what I've done here is I've taken the last set of 9 points or 10 points and the bottom set of 9 points. What I'm going to do is, if this is, let's say, the set of 3 points, in the first case I will take this point and I'll take this point and I'll find out their z coordinate, subtract them so that we get this, that is, we call it as delta z. Also find the length of this, which we call as hypotenuse. Now if we have the perpendicular or delta z and the hypotenuse, I'll get this angle, and if I do an arc sine or a sine inverse, I can get the angle of this or the slope of this. Okay, so again we get these points, and we're doing this not for 2 points at a time, but maybe 10, 11, 20, 500 points at a time. I've deconstruct this. I've got the z-axis, the z coordinate of both of them, subtracted it, and I have got the delta z, which is this. Okay, and then I have found the length between these 2 points, any of the 2 points, and I'll call that the hypotenuse. Okay, and what is happening here is I divide them so that I get delta z by h. Also in school we used to call it perpendicular by h, and that gives us the opposite angles, sine inverse. Now in sine inverse in Grasshopper language is called arc sine, and that goes into it comes out as radians. I give it as degrees, and now degrees will give me each of these segments angles. Now you can see this is pretty steep, so 11 degrees, and then it gets flatter and flatter and flatter. It reaches around 0, and then I've taken somewhere I've taken an absolute. I don't remember. Yes, I've taken an absolute, so anything sort of negative z, delta z, will also be positive. That's what an absolute does. Basically it's doing this, all high school mathematics. So I do this, and I find an average also. So even though all of these, you find each of these angles, I find an average, and my average slope for this curve is 6.75 degrees. And the total length is pretty small because it's a direct line from these 2 points. It's 76 meters from this point to this point, 76.9. Okay, let's make this better. So what I'll do is I'll keep it as it is, but I will create a meandering path somewhere below. Okay, I'll enable this, and what is happening is I took that line, I divided this here at ground itself or at level 0 itself. I moved these points by using these components. This vector rotation by 90 degree, basically if this is the line, it moves it at this axis. So basically all these points are moving randomly left or right, left or right, left or right, and this is totally random. This randomization is called by this something known as a gene pool. This is a gene pool. Okay. Since I have, how many points do I have? I have 10 points. Sorry, I have 11 points. I can edit this and cause a gene pool of a gene count of 11. I don't need any decimals. My meandering is from -10 to +10. Okay, and now when I right click, I'll just have just random iterations ranging from -10 to +10. And what I've done is I've done this little culling. That means I don't want the first point to move, that is 0, and I don't want the last point to move. Now last in Grasshopper's language is -1. So I don't want these 2 points to move. I want these start and end points to be the same, but everything else meanders, and by using insert list, I insert these endpoints back into the list and I get this curve. Slightly complex, you can ignore this part, but what I'm trying to do is I'm trying to create a meandering path. The second thing is I project this all. Let me enable this. I project this all the way here. Okay, I project all the way to the surface. Divide this again by, let's say, more points. So if I have more points, I can get it more accurate. You can always see the initial projected line is this. Okay, and the initial data is this. But if I meander this and I go through the same code for this random iteration, I have 5.37 degrees, already slightly smoother than my straight line, but my length is a little bigger, 103, and here it's 76. So maybe it's a slightly longer path, maybe 25 meters longer, but it's definitely slightly smoother as well in terms of the climb. But I want to minimize both of them. Okay. Now what we're going to do is we're going to create a random thing which is called multiplication of both of them. They don't mean anything. When I want both things to be maximized, their multiplication will also be maximized. I call this num, or a number. And then I use this solver which is called Galapagos, which is the most amazing research tool within Grasshopper. And if I use this, it takes fitness, and what I'm trying to fit here is this number, this random number, which is the multiplication of this and this, both these outputs. I'm trying to fit or reach a good fitness of both these outputs. Okay, and genome is the pool it is playing with, and that is our this gene pool. Okay, this is our input or our set of infinite iterations, and this is our output that is trying to make fit. How do I start this? Keep a track of this, by the way. I'll double click on this and I'll minimize. Okay, make sure you minimize because we have to minimize the fitness and not maximize. We have to minimize this also, and we have to minimize this also. So their product, which is num here, that has to also be minimized. So simple, since we can only do this with one thing, I'll go to solver and I'll make sure I want to see all iterations, display all genomes in the Rhino viewport, and I'll start the solver. Okay, think, and please remember that this we started with 5.37 and 103, and let's see what the solver does. I'll start the solver and I'll start going through all of the iterations, and once I take it here, you'll also see that it started with some 602, whatever this random number is, and it starts to minimize. Okay, and it keeps minimizing. It does like millions of iterations. It's trying to reach this optimum path which is the minimum of both of these. Okay, so you can go as long as you want, but I don't think it's gonna reach anything. It's trying really hard. It's trying really hard under this, but it's probably not going to go beyond this. We can go for like a 50-minute or whatever, but I will stop it for now. Okay, and this is the last or the best iteration that it keeps. I'll click OK, and now if you see, with just a meager, I don't know, 8 meters extra, I am having 1.5 degrees lesser slope. So my straight path was 6.75, and now this path that you couldn't have found out earlier is 5.34 degrees, and 1.5 degrees is quite significant for this length. By just walking maybe 9 meters extra, 8 meters extra, you're making your path really comfortable to walk on. So what I can do is, if I have this projected thing, I can bake this. I always like to group here, and if I kind of bring back everything, this is my best path between these two. Hopefully it's not going through any trees. If it's going through any trees, you can always make sure that you kind of go a little bit around, but this is one of the ways that you get the best path, which is also the easiest to climb.